Hello, this is checkpoint 5.30, and we are looking at a region bounded by below by the xy or r or theta plane, above by the sphere, and on the sides by the cylinder. Set up the triple integral and cylindrical coordinates to find the volume of the region following the order of integration that they say. So dz dr d theta, dr dz d theta, and d theta dz dr. Again, if you had a choice, the preference would be dz first and then dr d theta last, because dr d theta kind of falls naturally as polar coordinates from cylindrical to polar coordinates. And so the other two are just there, I guess, for us to look at this as an exercise. Okay, let's first remember that our volume is the triple integral over whatever E is, and then we put 1 in the integrand dV. And remember that dV will eventually turn into R times the differentials in whatever order we need it to be. Okay, let's do a quick sketch of the region. So the region itself looks like it's going to be a cylinder with a hole drilled out of it. And you can kind of see that in the picture, but we can recreate something close to that. So there's the hole here in the middle. And all this other stuff on the side. So that hole in the middle creates kind of like a shadow or an empty shadow. So on a XY plane, and what we have here is the actual solid itself would be just within this washer portion of things. So there's a hole in the middle of this cylinder, and this is what we have left. So the hole is coming right in the middle there. Okay. Now, first we are going to integrate with respect to z, dz dr d theta. So if we just run along where the solid will exist, we're going to draw a line parallel to the z-axis, and we're going to hit the z is equal to 0 first. So in our dz dr d theta order, we're going to see that z is going to go from 0 to whatever this this sphere is. So what is that sphere? That sphere was x squared plus y squared plus z squared is equal to 4. If we rewrite that in terms of cylindrical coordinates, this is r squared plus z squared is equal to 4. So z is the square root of 4 minus r squared. And so that's going to be the top part of the sphere. We're not considering the bottom part of the sphere, so we don't need to worry about that negative. So this is 4 minus r squared, our limits. Now theta would be, or r would be, a radial distance, and we can, back like in polar coordinates, we can look at it in 2 dimensions. And we see this is going to go from 1 to 2. So our r limits go from 1 to 2. And then our theta goes all the way around from 0 to 2 pi. So that'll take care of all of this that we're talking about. So our volume here in this order is going to be 1. And then don't forget the extra r that pops up from the dv. And this order is dz, going from 0 to square root of 4 minus r squared. Dr going from 1 to 2, and then d theta going from 0 to 2 pi. Okay, so that is the first integral that we're going to be looking at. The second integral, they want dr dz d theta, dr dz d theta, and for that what we need to do is we need to look at what's happening here for the radial distance from out here. So the radial distance here goes from 1 to 2, and it's just constant. But if you take a look at different cuts here, This is always going to start at 1, but it's not going to go all the way to 2 all the time. It's going to depend on where you are, what your particular height, what your z value is. So our r limits will go from 1, that's the cylinder, inner cylinder, to this part of the sphere. So in this case, we want to solve for r out of the sphere. And instead of solving for, I guess we should be looking at this equation. Instead of solving for z here, we'd solve for r, which will give us the same thing. R is equal to square root of 4 minus z squared. So that's going to be the upper, or in this case, the outer limit, 4 minus z squared. Now, what is our z? What are the z limits going to be? So the z looks like it'll start from the xy plane, or they call it the r theta plane, but it stops somewhere over here. So we need to figure out what plane this thing stops at, and that happens in the intersection between the sphere and the cylinder. So the sphere here, we'll write the sphere in terms of r or z. We'll write it in terms of r squared plus z squared is equal to 4. And then the cylinder is x squared plus y squared. So x squared plus y squared is equal to 1. So that's equivalent to saying r squared is equal to 1. Now that's conveniently r squared over here, so we can just replace this with 1. 1 plus z squared is equal to 4, so that's z is equal to, this is going to be 3 with a square root. So that's the square root of 3 is going to be the z plane where you stop. So it's going to go from 0 to the square root of 3. Okay? And theta is still going to continue to go around, and this will help us think about what's going to happen in our last portion of this problem, because theta is again independent of r and z. So our volume can be expressed as a triple integral. The integrand is 1. The dv becomes an r times whatever order you have. So our dr goes from 1 to the square root of 4 minus z squared. Our dz goes from 0 to the square root of 3. And our d theta goes from 0 to 2 pi. Okay. All right. Let's attack that last one. And with that last one, we'll use that argument that we made earlier that theta is independent of r and z. And so if they want d theta, d z, dr, I'll just look at the order of z and r here. Z and r, I would use this order over here and then use these limits. And so using those limits, I would just switch the order. So theta would go from 0 to 2 pi like it's always done. And then the z goes next from 0 to the square root of 4 minus r squared, and then our r goes constant limits from 0 to, or from 1 to 2. Okay, so the integral v is going to be the triple integral 1 r and then d theta from 0 to 2 pi, dz from 0 to the square root of 4 minus r squared, and dr goes from 1 to 2. All right. Like always, if we had a choice, we want to definitely go with this dz, dr, d theta. Again, the cylindrical coordinates is really an extension of polar coordinates, and polar coordinates are r theta living in the xy plane. And so it's always natural to look at r and theta as the last set of integrals. That makes the z the first set of integrals to do. And doing it, switching the order, is really just a mathematical exercise of being able to describe your solid region as the different variables change. All right, I hope this helps.